Okay, hi everyone. Welcome to today's lesson. It's going to be a recorded lesson because I'm going to work through just to review some of the concepts that we left off at the end of last week. But before I get into that, I just want to say thank you all for being adaptable and flexible and watching this video as part of today's lesson. Just a couple of quick reminders. You should have already submitted a photo or scan of your final draft of the Atomic Box project to the Atomic Box project assignment on Google Classroom. So if you haven't done that yet, please do so. And then also, you've got now 5 attachments to your atomic bonding homework folder on Google Classroom as well. So I will be checking that folder to see that all 5 of those assignments have been completed on Friday. So please make sure you've done that between now and then. So I guess before we get started, I hope you guys enjoy my study here. I'm kind of looking like a little bit of a deer in the headlights. But anyway, let's go ahead and get into ionic bonding. So right before the break, we were talking about chemical bonds. Okay, chemical bonds are what holds atoms together when they create compounds and molecules and eventually larger structures like polymers and crystals. And the first type of bond that we've talked about so far is called an ionic bond. This occurs between a metal. As you will remember, are the elements that fall on the left-hand side of our periodic table to the left of this orange semi-metal staircase. And then our nonmetals, which is everything to the right of that semi-metal staircase, or what they say in this graphic, metalloids. So if you've got a metal and it's combining with a nonmetal, the way that those two atoms are going to be held together is through an ionic bond. So, the name ionic bonding comes from the fact that ions are produced in this process. You'll remember that an ion is an atom that has some sort of an electrical charge on it. It can be either a positive charge or a negative charge. So as we stated earlier, the first ingredient to these bonds are metals. And metals are always going to form positive cations. So if you're looking at your periodic table, hopefully you've got that on hand, and if you don't, just press pause on this video and go and grab it. But you should remember that most metals on the periodic table typically have between 1 and 3 valence electrons. So they kind of want to reach 8, but it's harder for them to gain electrons to go all the way up to 8 than it would be just to lose electrons. So a great example of that would be magnesium. So I've got a picture of a typical magnesium atom here. This is before anything's happened. It's a neutral atom, which means we've got 12 protons in the nucleus, 12 electrons in the orbitals surrounding the nucleus. And so you've got 12 positive charges being canceled out by 12 negative charges. We've got a nice neutral metal atom. Okay. Now, essentially, what's going to happen is 2 of those electrons are going to be given away. Remember, when we're talking about bonding, we're talking about these electrons here, our valence electrons, or the electrons that land in that very outermost ring, that outermost orbital. So again, this neutral metal atom is going to lose these 2 valence electrons to whatever non-metal it's combining with. And when it does that, it becomes a cation. So over on this right-hand side, you can see a magnesium cation. It's lost these 2 valence electrons, which means this 1, 2, 3, third orbital has completely disappeared. You'll notice this one doesn't even have a third orbital. It's down to 1, 2, since those 2 electrons that were out here have been given away. The result of this is that you end up with a magnesium atom that's got 1, 2, 3, 4, 5, 6, 7, 8 valence electrons in its outer shell. So it is happy. It is nice and stable. Okay, but what's going on as well is that you still have those 12 protons in the nucleus, Now we've only got 10 electrons orbiting, so there's a mismatch here. We've got more positive charges than we have negative charges. And we call that a cation. So again, what this means is that the metals are going to have more protons than electrons. They're going to end up with a net positive charge, and an atom with a positive charge on it. You can see, like I said, this magnesium will have a charge of +2. Any of these ions with a positive charge are going to be referred to as cations. Okay. On the flip side of that, we've got our nonmetals. Okay, nonmetals, as you recall, are found on the right-hand side of the semi-metal staircase on the periodic table. So, they have between 4 and 7 valence electrons. Okay, so you can see this oxygen atom, it's between 4 and 7. It's got this 1, 2, 3, 4, 5, 6 valence electrons. So it's in that range. Now, in order to get to 8, it's going to be able to gain electrons to get to 8. It's much easier for this oxygen atom to say, ooh, I've got 6, I want 8. I'm just going to pick up 2 more rather than trying to get rid of these 1, 2, 3, 4, 5, 6 electrons. Okay, so it's going to accept a couple of valence electrons from the metal that it's bonding with. Those electrons are going to come into this valence shell, and it's going to end up with 8. 1, 2, 3, 4, 5, 6, 7, 8. And remember, anytime an atom can get to 8 valence electrons in its outer shell, it becomes much more stable. It's much more happy. Okay, so this is one nice stable oxygen atom. Okay, but again, we're not quite done. When we originally had 8 positive protons and 8 negative electrons, now we've got 8 positive protons but 10 negative electrons. So again, with more negative charges than positive charges, you're going to end up with an ion. You're going to end up with a charged atom. And in this particular case, with more electrons than protons, you're going to end up with a negative charge on your atom. And we call any of these negatively charged ions anions. So again, that means that nonmetals will have more electrons than protons, will end up with a net negative charge. And anything that's got a net negative charge on it, we refer to as an anion. Okay, so now we've got our metal cation, our magnesium that we said ended up with a charge of +2 on it. We've got a nonmetal anion, an oxygen atom that has a -2 charge on it. Okay, so these oppositely charged ions here, my cation and my anion, they are going to bond together in order to form a neutral compound. Opposites attract. So, again, a positive plus a negative is going to end up with a nice neutral compound. So we started with our magnesium, we combined it with oxygen, and we end up with magnesium oxide, or as represented by the chemical formula MgO. Now, when we go ahead and name these compounds, again, we always write the metal cation first. So keeping with our magnesium oxide example. Okay, our metal that we started off with was Mg, or magnesium. We're going to keep that element name the exact same, still calling it magnesium. Okay, we've combined that with our nonmetal, our oxygen. This is where we make a change. Rather than calling it oxygen, as we did before, we're going to change the last syllable of the non-element name to "ide." So oxygen, we lose the gen and we add "ide" to get oxide. We put those two together and the name becomes magnesium oxide. Now, a lot of students, while doing their homework, have asked me, what should I do if the charge strength of the cation and the anion are not equal? And that's a really, really great question. So, in our charts here, we can see kind of what's going to happen to these different atoms based on how many valence electrons they start off with. So remember, our metals are going to form cations with positive charges. So any elements that are in our first group, group 1, that first column on the right-hand side of the periodic table, including lithium, sodium, potassium, rubidium, cesium, and francium, they all have one valence electron here. Okay, they're going to lose that valence electron, and when you lose a negatively charged electron, then you're going to end up with an ion with a positive charge, +1 on it. Okay. In group 2, however, okay, that's our second column on the right-hand side of the periodic table. That includes elements like beryllium, magnesium, calcium, strontium, barium, and radium. Okay, those all have 2 valence electrons that they are going to lose. So again, if you lose 2 electrons, each with a negative charge on it, then you're going to end up with a charge of +2. Okay, because you have now 2 more protons than you do electrons in that atom. So it'll end up with +2. Okay, our transition metals are a little bit strange. They can form a couple of different types of ions. So their charges end up being +2 to +7. I'm not going to get into that right now because it is complicated. Okay, so let's just skip these groups for now and look at group 3. Okay, so group 13, these all have 3 valence electrons. So if you skip the transition metal block and start looking at that column that has aluminum, gallium, indium, and thallium, those all have 3 valence electrons that they are going to give away. Okay, so if you give away 1, 2, 3 negatively charged electrons, you end up with a positive charge of 3. For our nonmetals, okay, same thing, except for we're going to end up with negative charges because they're gaining those electrons that the metals are losing. So carbon starts off with 4 valence electrons. In order to get to 8, it can accept 4 more valence electrons, each bringing a negative charge with it. So you're going to end up with an ion with a negative charge of 4. Okay. In group 15, elements with 5 valence electrons, including nitrogen and phosphorus. They have 5 valence electrons. They can accept 3 more to reach that magic number 8. And if they get 3 more negative electrons, they end up with an overall charge of -3. Group 16, those elements all have 6 valence electrons. So oxygen, sulfur, selenium, they all can fit 2 more. If they get those 2 negative electrons, they'll end up with a charge of -2. And then lastly, our halogens in group 17, those all have 7 valence electrons. They can only accept 1 more to reach 8. So that includes fluorine, chlorine, bromine, and iodine. If they can get that 1 valence electron that they're looking for, it'll come with a negative charge, and they will end up with a negative charge of 1. So it's really, really important to remember that not all ions have the same strength of charge. Okay, so let's, for an example, take a look at magnesium. Okay, so how can magnesium, that's going to end up with a charge of +2, be able to form an ionic bond with iodine that only has a charge of -1? Okay, how can we make a cation with a charge of +2 bond with an anion with a charge of -1? And the answer to that is when you combine these substances, you usually have a bunch of magnesium atoms and a bunch of iodine atoms present. And so what we're going to do is we're going to need some extra atoms. So what will happen is, since magnesium has a +2 charge on it and iodine has a -1 charge on it, each magnesium atom is going to bond to 2 iodine atoms. So let's just kind of look at how this entire process works step by step. Okay, we start off with our magnesium atom that's got these 1, 2 valence electrons. Okay, we have 2 iodine atoms, each with 1, 2, 3, 4, 5, 6, 7 valence electrons. Okay, so magnesium's trying to get rid of its 2. Iodine needs to get 1. This iodine also needs to get 1. And so it's actually a match made in heaven. So what's going to happen is magnesium has 2 valence electrons it's trying to give away. Each iodine atom needs to get 1 valence electron to reach 8. So the metal magnesium atom is going to donate 1 valence electron to each of the 2 nonmetal iodine atoms. And in this process, all 3 atoms become more stable. Okay, so you'll see magnesium gave away its 2 valence electrons. Now it would actually technically have 8 because we'd be going to an inner orbital here with 8 valence electrons. And now iodine's got 1, 2, 3, 4, 5, 6, 7, 8, the 8 valence electrons that it is looking for. So all 3 of these atoms, 1, 2, 3, are all really nice, happy, stable atoms. Oops. Okay. Didn't quite finish my animations, I guess. All right. So step 2, okay, by losing those 2 valence electrons in step 1, the magnesium atom is now going to end up with a charge of +2, and gaining an electron gives each of the iodine atoms a charge of -1. So this is now positively charged 2. This one's got a charge of -1. This one's got a charge of -1. Those opposite charges are going to attract one another. They're going to stick them together due to the electromagnetic force, and this is an ionic bond. And so now we've got ourselves magnesium iodide. With every 1 positively charged magnesium atom, we're going to have it bonded to 2 negatively charged iodine atoms due to that difference in their overall charges. Okay. So what I would like for you all to do at this point is see if you guys can kind of work backwards using this idea of having to use different numbers of each ion to reach a neutral compound. So what I've done is I've provided you all here a bunch of names of ionic compounds. And I want you guys to figure out how many of each atom is going to be needed to create a neutral compound. So for example, I've given you sodium chloride. By looking at your homework assignments, looking at your periodic table, you're going to look and see, okay, what is the charge on a sodium ion going to be? Remember, sodium's a metal, so it should be positive. Okay, it's got 1 valence electron, so it should end up with a charge of +1. Chlorine is a nonmetal. That's going to gain electrons. It should end up with a negative charge. Chlorine's in the halogens. It has 7 valence electrons. It's going to gain 1, so it should end up with a charge of -1. So if sodium's got a +1, chlorine's got a -1, you should only need 1 of each of those atoms to make sodium chloride. So your formula should end up NaCl. Okay. Now that's a little different from sodium oxide. You may find that you need more atoms of sodium to cancel out the greater charge of each oxygen atom. All right. So at this point, work independently. I'd like you guys to do your best on this. If you're watching this video and you need a little extra time to go through before the answers are shown, press pause now because in the next few minutes or so, the answers to this will come up. So press pause, work through these, and then check your answers in the next section of the video. Okay.